right, guys. Well, I think it's 4 o'clock, so I think I'm going to go ahead and get started here. Welcome to a new month. We are into March, if you can believe it. And that means we're close to halfway through the semester. It also means I'm about to get a year older again. Uh, but that's okay. Anyway, yeah, so let me just make a couple of announcements as we get started here today and let you know kind of what's coming up. First of all, I will remind you there's homework due tonight, and a few people have already got a couple questions on the board over there, so I'll probably try and save a little time for that. The very last two problems on the assignment, did you all get my little email with the video on that? Was that video okay? Okay, I only saw 6 likes so far, but I'm sure you're all still waiting to get that done. Anyway, I just want you to maybe watch that video and just use that as a guide to do those last 2 homework problems. But of course, if there's any questions on it, if you don't understand anything out of that video, I hope that you won't hesitate to follow up with me during my office hours. So I do have office hours, of course, tonight after 8 o'clock. When I'm done with my other class, I'll be down there most all of the evening with a dinner break at about 9, my usual routine. So you can come in right after my class at 8 and ask some questions, or you can come in after 10 in person, in Zoom. Either way, I'll be around, and I'm really always happy to answer questions. So I'll try to do a couple of them for you all here together in class today. I'll save a little time just to mix things up a little bit as well. So hopefully that'll help out. So what's coming up next? There is another assignment that is currently listed as being due on Friday. I want you to treat it like it's going to be due on Friday. I'm not sure for sure if it will be due on Friday. The reason is, I think you guys all know that I'm a mountaineer. I go climbing mountains as a hobby, and I have had plans to go up to the state of Washington to climb Mount St. Helens. For 4 years, I've been trying to climb this mountain. It's not even that high. It's like 8,000 feet, and it's not all that high. I've climbed mountains that are much harder than Mount St. Helens. But first there was COVID. I had to cancel the trip for COVID. Then the next year, it snowed the entire month, because it's usually March is the best time to go. It snowed for the whole month of March. Then the next year, I got sick. I couldn't go. The next year, which was last year, it turned out to be like 50 to 60 degrees on the mountain. And I have a buddy up there who I'm supposed to be doing this with. He says, everybody says, don't do it. The avalanches are going to be bad because all this snow was melting. It was too hot. So I have been shut out on this mountain so many times. It looks like there's a decent chance I may get to go do it, though, this weekend. So if that happens, I will be leaving on Friday morning early, and I'll be pretty much in the wilderness Friday and Saturday. Then I'll be back in, civilization by Sunday. So if that were to happen, I would probably end up trying to move the homework to Sunday and having some office hours on Sunday. They might be Zoom office only hours, but I would like to try to have some office hours before I make you turn in the next assignment. So stay tuned on that. I think you should try to start the homework before Thursday. I can obviously answer questions in class on Thursday. We're not going to be missing any class over this. It's just, I don't like to have people having to turn in homework on a day when I'm completely unavailable. So I may change the date just to help out with that. But I don't know yet because the weather changes on a dime around here. So anyway, we'll see what happens with that. Also, next weekend, well, we're 2 weeks away from another midterm, and I am going to ask you to watch another extra credit video. Remember how we did this for the first exam? It seemed like you guys were okay with that. So I would like to do that same rinse and repeat thing again this time, except I'm going to have you watch the video before the midterm. So you should plan on that for this coming weekend, that you're going to earn 4 points towards the next midterm by watching and submitting notes on a video. So you don't have to do any problems. You just have to watch the video, take the notes, and submit them in. So I'll send you what that is. It's basically going to be an introduction to inner product spaces, which is coming up in chapter 5. But it'll be a little bit over an hour again. So it'll take you a little bit of time. And this coming weekend, we lose an hour because I think they're going to make us change the clocks forward. So just plan on that a little bit. So that will be coming coming up next weekend for you to do. Okay, but I'll send out an email. I'll send you the link and all that so you'll know what to do. Okay, there will also be an extra credit quiz coming, but that might be next week sometime. I'll probably wait till next week for that. Okay, I think those are my comments for now. Does anybody have any questions? Yes.
It's just a fun question. Have you ever did like office hours in the mountain?
On a mountain, very rarely do I have cell phone signal on a mountain. I would love to. If I could do that, I wouldn't have to change any of my homework deadlines. It's not very common to have a good signal up there.
I'm getting Starlink.
I have a GPS that I always take with me. So it's a satellite receiver that I can send emergency messages, but I'm not sure a 250B homework counts as an emergency. The Garmin people are gonna, start looking at my messages saying, what's this guy bothering us with? So anyway, yeah, no, good times. Anyway, if I'm able to go, I will definitely take pictures and show you. I really enjoy the scenery. So, okay, if there's no other questions, guys, I'm gonna get started by recapping what we were doing on Thursday last week and kind of get started again from here. And we're getting close to the finish of chapter 4, believe it or not, this long discussion about vector spaces. But if I give you a set of vectors in a vector space, right? There's a couple of questions that we were focusing on last week that I want to bring back to the surface again. 2 questions. First one is S a spanning set for V? That just means, does S span V? It's another way to say the same thing. So is it a spanning set for V? And then the second question is S Li? Linearly independent. Both of these should be thought of as good things, right? It's good to find a spanning set for your vector space, and it's good if it was as cheap as possible. Remember, linear independence is sort of the idea that you don't want to just throw in a truckload of vectors into a spanning set. Every vector costs you $1,000. You want to make the cheapest possible spanning set that you can. So you'd really like to have a yes and a yes out of these 2 questions. Turns out that the tests that we have for answering these questions are very similar, right? They're very similar. We need to set up a matrix, okay? And the way this works, guys, is that you're going to lay the vectors that you're given, you're going to lay them into the columns of a matrix. And you're going to augment that matrix either with number symbols, that's for the spanning question, or you'll augment it with zeros if you're answering the Li question. Now, as you saw last week, what I usually like to do is combine them together. And it goes, you remember why I did like the 0/ number symbol thing? So that you can just do the EROs once. Because you do have to bring this matrix into row echelon form and look at the pivots. The pivots are the key to deciding whether the system is consistent or not, and whether there are any free variables or not. And that turns out to be the deciding factor as to whether your answers over here are yes or no. So I've just kind of summarized it right here. If you sort of want all in one place, a big summary of last week, this is it. This is a pretty good kind of short, to the point summary of what's going on. Now, of course, we have to practice this because sometimes we have polynomials, sometimes we have matrices, sometimes we have physics vectors. So it looks a little different in terms of the notation and kind of how it plays out in terms of what you're writing down, depending on the example. So I would like to warm up today with a few examples of this again. Okay, so we've already done some last week, but I just want to kind of take it easy on this and just try a few more of these. Okay, so here's my idea. I'm going to give you a set of vectors. I'm going to call it S. I also have a vector space here. And I would like to decide, is S Li, is it a spanning set, or is it both, or is it neither? We even did, I think, some group work last week on this. So you guys have had some chances to practice this already. Just want to practice it a little bit more right now. So, okay, so let's go ahead and let's just try a couple of these. Let's start with number 1. Just see what we can do with this problem number 1 here. Again, what we're gonna do, guys, on number one, we're gonna take P2 of R, and notice that we're gonna take these two polynomials. I'm gonna lay those polynomials into the columns of this matrix, but of course, I'm actually just going to take the coefficients. So x squared minus 2x plus 5, I could write that as a 1, and then a -2, and then a 5. Okay, by the way, be careful if some of the powers of x are missing. You still have to put those in your matrix as zeros. So like if this was x squared plus 5, if it was x squared plus 5, you would still need 3 slots here. It would just be that the middle slot would be a 0 in that case. Okay, so just make sure some people have been getting the wrong answers on the homework, and the first thing I always look at is, well, let's see what matrix you set up, because sometimes if there's zeros that should have been there, that's a kind of an easy thing to make a mistake with. The second polynomial would be a 1, 1, and 7, and then I'm going to augment this with 0 slash number symbol. This is a slash notation. It's not dividing. Okay, just to be totally clear on that, I'm not doing any dividing here. I obviously have a pivot right here. Okay, and I am going to do some EROs. I'm going to do A12 of 2 and A13 of -5. So the first row is going to stay exactly the same. If I take 2 times the first row and I add that to the second row, I will get my 0 in this second row here, and then this will be a 3. And then remember that 0 slash number symbol just stays the same. It doesn't ever have to change. You don't even have to think about what's happening on the far right side. Okay, and then I said A13 of -5, so this would be a 0, a 2, and a 0 slash number symbol. Okay, I'm still not done because I can't have a pivot directly below another pivot. So I'm going to go one more step here. I'm going to do A23 of -2/3. So the first 2 rows are going to stay exactly the same. So I am doing the EROs fairly quickly because I just don't want to dwell too much on this. The point is you're going to get a 0 and then a 0, and then a 0 slash number symbol. And when I read that bottom row, if I'm dealing with the number symbol there, that actually becomes my pivot. That actually becomes a pivot because you've got zeros to the left of it. And so this is our final matrix. So let's ask the questions over here. Is this consistent or not? Nope. It's not consistent. It's not consistent because there's a pivot in the far right column. So this is going to be a no. It's not a spanning set. Okay, so it's not a spanning set. Let's ask about free variables. Are there any free variables here? No free variables would occur if there were unpivoted columns, and there are not. Every column has a pivot. So there are no free variables. That's a yes on the LI question. So this one is going to be LI only. LI only on number 1. Okay, it's linearly independent, but it's not a spanning set. Sense? By the way, you might remember I made a remark last Thursday about when you have only 2 vectors, and we only have 2 vectors here in this first example. When you only have 2 vectors, there's actually an easier test for LI. If you remember, I wrote it in the notes. It was just simply that they're not scalar multiples of each other. So as long as you can't take one of these polynomials and multiply it through by a number and get the other one, then the vectors will be LI. So I could have figured that out just by glancing at this. I didn't really need to do the whole matrix thing for the LI question. But since I was trying to test everything, it didn't really cost me anything to write out the whole matrix here. Okay? Any questions on this one? Let's try the next one. Let's go on to number 2. On number 2, my vector space is R4, and I've got my vectors here. Let's make the matrix right away. The first column is 1, 0, 0, 1. The second vector is 2, 0, 0, 4. The third vector is 0, 3, -1, 2. Then we have 0, 1, 0, 1. And then we have 1, 3, 2, and 6. And I'm going to augment this with 0/number symbol. Okay, so this is our setup for our matrix in this case. And obviously, again, I need to do some EROs on this. I think, would it be okay with you guys if I just sort of tell you what the row echelon form is? Let's skip the details. It only takes about 3 or 4 steps, but I'll just write the word check here. You guys can kind of check this. This is not the interesting part. The first row is, of course, already good to go. So I will go ahead and I can even circle my pivot there in the first row. There's nothing that's going to change about that. But then at some point I permuted this bottom row up to the second row, and then I did an ERO on it, and I got 0, 2, 2, 1, 5. Okay, so there's my pivot right there on top of that 2. The third row is actually the same as the third row that we already had, so that ends up not really changing at all. So 0, 0, -1, 0, 2. And then the last row turns out to be 0, 0, 0, 1, and 9. And again, I'm circling those pivots for you. So just take my word on this one, that this is going to be your row echelon form. So if you're willing to trust me on that, what would you say? Is this a spanning set? Is it LI? Is it both? Or is it neither? Spanning set. Why is that? There is a free variable right here, so that's bad. That means LD. If there's a free variable, it's LD. And it is a spanning set because the pivot did not go all the way to the far right column. So this one is spans V only. So this one's a spanning set, but it's not LI, right? Okay, so far so good. Let's do number 3. Let's do number 3. Number 3 is the vector space is R3, and the set S, we have first column is going to have a 1, 1, 1, and then 2, 0, 6, and then 4, 2, 2. And again, we augment this with 0/number symbol all the way down the line. Okay, that's what we're actually going to have there. And in this case, okay, I could do the same thing again. I could do the EROs, but I have another option this time. I'm wondering if anybody can tell me what tool do I have with this matrix that maybe I didn't have on the first 2 that I could maybe take to my advantage right now. It's a square matrix, right? The left side of that bar is 3 by 3. And so I can actually take the determinant of this. Okay, and since it's 3 by 3, you could actually use the arrow method if you wanted to. I am just going to tell you, I went ahead and did this before class. It turns out that this determinant is not 0. Just take my word for it. If you do your arrow method, 0 + 4 + 24 -0 -12 -4, it doesn't cancel out. Okay, so it's not 0. If it's not 0, that basically means that if you did the EROs, if you did them, we're not going to do them, but if you did them, you would get an invertible matrix where the pivots are going right down the main diagonal, right? So the far right side is unaffected by any of that. But this is the way it would work, right? Remember, if the determinant is not 0, what all does that mean? It means that the matrix is invertible. It means that the matrix has rank 3. It means that it is row equivalent to the identity. Like all of those things, remember from the list A, B, C, D, E, F, and so on, right? So this is one of the things you would conclude, that for an invertible matrix, that's how your pivots are gonna shake out, right? And based on this, what would you say? Is it LI? Is it a spanning set? Is it both, or is it neither?
Both.
It is both. This one is both. That is absolutely right. That is absolutely right. So this one is both. And that's actually good. That means that we have found a spanning set that also happens to be as cheap as possible. Okay? there's actually a word that we use for a set that is both. And it's one of the most important words in the theory of vector spaces. It's called a basis. A basis for that vector space. And I want to write this down. This is technically in the next section here, which is what Friday's homework is about, 4.6. And what it is just for a definition. Definition here, guys, a basis. A basis for a vector space V is a set S of vectors such that a basis for a vector space is a set S of vectors such that the first thing is S spans V. That's just another way of saying it's a spanning set for V. And the second condition is that S is Li. S is Li. Okay, so in other words, both. Anytime you're circling both on one of these multiple choice 4-part questions, you're really saying that S is a basis for V. So we might as well use this last example as our first example of that. So the set 1, 1, 1, whoops, sorry. The set 1, 1, 1, and then what was it, 2, 0, 6, and 4, 0, 2 is a basis for R3. That's a good example. And again, the reason it's a basis is that it was both. Why was it both? It was both because the way these pivots went right down the main diagonal. Why did we know that that was going to happen? It was because when I put those vectors into the columns of this matrix, the determinant was not 0. That was actually really the reason. That was ultimately, if you want to boil it back down to the essence of the issue, when I put these 3 vectors into this 3 by 3 matrix as columns, that matrix was invertible. So, question for you. Do you think that's the only basis for R3? I mean, wouldn't you agree that I could make any 3 by 3 matrix as long as the determinant was not 0 and I should be fine? Right? Let's see if we can make another one. I'm just gonna think this. Maybe I'll scribble over here. How about if I do 1, 2, 3, 0, 4, 5, 0, 0, 6? Would you guys all agree that that's invertible? Yeah. Okay, so there you go. The set 1, 0, 0. I'm grabbing the columns here. 1, 0, 0, 2, 4, 0, 3, 5, 6 is a basis for R3. There are billions of these things. There are billions of them. What might be the easiest one? Like if you had only one answer to get you off of a desert island, what would maybe be the most simplest possible basis for R3 that you could think of?
1, 0, 0, 0, 1, 0, 0, 0.
1, 0, 0, 0, 1, 0, and 0, 0, 1. This is so natural that this is actually called the standard basis. So you will sometimes see me talking about a standard basis. This is called the standard basis for R3. Okay, it's a standard basis. And of course, if I put this into a matrix, it does not get much more invertible than the identity matrix itself. Right? So you're good to go with that one. Guys, there's millions of them. There's millions of bases for R3. This is somehow maybe the easiest one, but there's gobs of them. Gobs of them. It's kind of the problem with this class sometimes. There's just more than one right answer. right? You can't just check the back of the book and have the answer there, because there's just so many of them. I mean, all you gotta do, you could spend from now till midnight writing down 50 of these 3x3 matrices that are all invertible, and you'd have 50 different bases for R3, right? Okay, although there are many, many different bases for R3, is there something about each of them that you think might be in common among them? Is there something that's the same about this basis as it is to this one, as it is to this one?
Is it the same number of vectors?
The same number of vectors in the bases. That is critical, and that's exactly what I wanted to point out. So let's make that as a little remark here, right? So the remark is a vector space can have many different bases. So by the way, the plural of basis is bases. It's not bases. So the plural of basis is bases. A vector space can have many different bases, but they all must share the same number of vectors. I mean, does that make sense? It should. If I only had to spend $3,000 to span my vector space, would it make sense that somebody else is going to come up with a both answer with 4 vectors? That would mean that they spent $4,000. This is more than I spent. That doesn't sound too good. Something's wrong, right? Chances are that the vectors they have are LD, right? On the other hand, if somebody else came along and only had 2 vectors in their hands, we had only 2 vectors here, that doesn't sound like enough vectors to span R3, right? I mean, after all, if they could do that, let's just play devil's advocate. If I can span R3 with only 2 vectors, then each of these would have been spending too much money, and I would not be too happy with any of them. I wouldn't be calling them a basis. So yeah, there is this number that we want to associate with a vector space now, and there is a name for this correct number of vectors here. And I'm going to make a definition. Maybe let me come back over here. Just want to make sure we have enough room to see it. Yeah, is everybody with me so far tonight? Am I making a little bit of sense? I didn't sleep very well last night, so if I'm rambling too much, it's probably just that. That's okay. There's nothing will wake me up like a math lecture, that's for sure. So yeah, so definition here, the dimension of V, which is written dim of V, is the number of vectors. It is the number of vectors in any basis for V. It is the number of vectors in any basis for V. Right. And so just with the example that we've already looked at, we obviously know already that the dimension of R3 is going to be 3. So we have our examples. We have 3 bases here for R3. Okay, that's the correct number of vectors. Okay. Now, if I'm going to answer both right here, you notice the pivots, they have to go right down this diagonal, don't they? On the previous example, it did not quite work out. Okay. On the example above that, it also did not quite work out. And you know what one of the problems is? Does everybody see there is a problem here? Do you notice the size of the matrix here? Right? I mean, you don't even have a main diagonal in a matrix that's 3 by 2. And this one is 4 by 5. you also don't have a main diagonal there. In fact, I can guarantee you that even before you work on this problem number 2 here at all, I can already tell that there must be a free variable. Because you got too many columns. 5 columns, at best you'll get 4 pivots. So you're gonna come up short, guaranteed. The matrix is not a square size. If the matrix has more columns than rows, you are guaranteed that your vectors are gonna be LD. And if you have more rows than columns, then you're gonna be guaranteed that your vectors are not gonna span the space. That pivot is for sure gonna be drifting off into that far right column. So it really requires you to have a square. If you wanna have a basis, if you wanna be both Li and a spanning set for V, you really need this left side to be a square size matrix like it was on this example. Okay. With that in mind, does anybody want to take a guess about what the dimension of, let's just say R4? What do you think the dimension of R4 should be? I mean, here we have vectors in R4. How many vectors do you think we would have needed to have to be able to even have a conversation about a basis for R4? 4, right? If I only had 4 vectors, in fact, if I literally just kind of cross this off, well, then I've got, a 4 by 4 matrix, and I could end up with pivots down the main diagonal, and then I would have both, right? And that would be good. Yeah, so this is 4. This is 4. More generally, let's see if I can press my luck with you guys. What do you think in general for Rn that the dimension would be? It's going to be n. That's exactly right. It is going to be n. Okay, so that seems pretty reasonable. By the way, you're going to want to memorize these kind of numbers. You're going to want to know them cold. You're going to want to know exactly how many vectors should be in a basis before you even have to think about anything else. Just like, what's the dimension of the vector space? And then you can take whatever the question is and go from there, right? This is somehow measuring the size of your vector space. The dimension tells you, well, how many basis vectors does it take to span V? Like, what's the minimum you can get away with, right? That's what this dimension is really talking about, okay? Let's do another example. One more example here. I wanted to write it down earlier and I just forgot to write it down. Let's try this one. So another example. Lots of examples here. So I'm going to work with M2 of R for a moment. M2 of R, and I'm going to give you some vectors here. S is going to be, now I have a list of some 2 by 2 matrices. 1, 0, 3, 4. And then comma, 0, -1, 0, 0. And then comma. And then the next one is going to be 2, 2, -1, -1. And then the next one is going to be 1, 3, 3, and 0. Okay, so let's make that our set S. And I'm going to go back to that original question again. Is S Li spanning set both or neither? I want to go through this. I want to go through this exercise one more time. So when we're doing this, guys, is it okay if I write down here? You guys see okay back there? Yeah. All right, perfect. I'm just going to put this right here. Each of these 4 vectors has to be sort of smeared out into a single column. So this first matrix, which is 1, 0, and then 3, and then 4, I'm going to lay that down as 1, 0, 3, 4 into a single column. Now, do you have to go upper left, upper right, lower left, lower right? No, you don't have to list them in that order, but what you have to do is be consistent from one matrix to the next. So if I usually do go left to right and top to bottom. So 1 and then 0 and then 3 and then 4. So on the next matrix, I do the same thing. 0, and then -1, and then 0, and then 0. Okay. And then on the next matrix, I do the same thing, 2, and then 2, and then -1, and then -1. And on the last one, same thing, 1, 3, 3, and 0. And I augment this with 0 and number symbols. 0/ number symbols all the way along. Just like that. Okay. And I actually can circle, the first 2 rows have pivots that go down to the right the way they're supposed to. I technically do need to do an ERO here. Or what's my other option, by the way? It's a square matrix, right? Just like this was a square matrix, and what did I do over here? To determine it. Maybe I'll do that, okay? Maybe I'll do that. Let's take the determinant of A right here. Well, if we cofactor expand the second column, life will be good because there's a ton of zeros in that second column. You guys remember how to do determinants here? So we have to expand, I'm just going to write that down. I'm going to expand column 2. Expand column 2. So I have a -1. And then that has to be multiplied by the determinant of the 3 by 3 matrix that I get when I cross off that second row and second column. So I'll have a 1, 2, 1 on the top row, and then the next row is 3, -1, and 3, and then the third row is 4, -1, and 0. And that can be accomplished with the arrow method. I'm just going to skip that and let you guys check. It turns out to be 28. So you have a -1 times 28, but the most important thing about it is that it is not 0. It is not 0. And what that means is that if we had done the ERO process over here, we would have gotten pivots going all the way down the diagonal, just like we did here. And so what would the answer be on this question? It would be both. It would also be both. That's exactly right. Oh, so that means I have a basis for M2 of R. This set S is a good example. Let's write that down. That S is a basis for M2 of R. So now we're working on matrices, and just as a note, the set consisting of, I am going to write it out one time here, guys, 1, 0, 3, and 4, comma, 0, -1, 0, and 0, comma, 2 and 2, and -1 and -1, and comma, 1, 3, 3, 0 is a basis for M2 of R. That is a basis for M2 of R. And if you believe that, well, I did all the calculations correctly, but if you believe that, I think that means that we should be able to write down the dimension of it. Let's just do that here, guys. So what would be the dimension of M2 of R? How many vectors does it take to make a basis for M2 of R? Listed right there, isn't it? 1, 2, 3, 4. There's 4 of them. That's exactly it. And just like with R3, this is not unique. There's many bases for M2 of R. Let me just make another little observation. Example here. There is also a standard basis for M2 of R, which would be the one that has all the 1s and 0s in it. So you'll have 1, 0, 0, 0. Comma, 0, 1, 0, 0, comma, 0, 0, 1, 0, comma, 0, 0, and then 0, 1. And that guy right there, this is the standard basis for M2 of R. Basically, it's, if I'm calling it the standard basis, what that really just means is that if you were to throw it into a matrix the way I've been doing, that you actually literally get the identity matrix right away. Right? If you lay out these 4 matrices, just like we were doing on this example, it is immediately the identity matrix. You don't even have to think about an ERO here. You don't have to take a determinant, you don't have to do an ERO, it's just kind of obvious. This makes sense? Let me try you on another example then. What do you think would be the dimension of Mn of R? Okay, so I'm jumping ahead now. I'm saying, well, what if my matrices were 3 by 3 or 4 by 4 or 5 by 5? I'm wondering if anybody has an idea. I know you have an idea, but let's see. How many people think they might have a guess? Did you maybe have a guess? Alex?
N squared.
N squared is that what you were gonna guess?
Yeah.
And you? Nice, that is exactly right. Guys, if you think about it, if it's a 3 by 3 matrix, you'll have 9 entries. And so there'll be 9 different places that you could move the 1 around into the matrix and fill out the whole matrix that way. You see what I mean? So, I would have 1 0 0 0 0 0 0 0 0. That would be the first matrix vector. And you'd go all the way along, and the last one would be 0 0 0 0 0 0 0 0 1. And there'd be 9 of them, because there's 9 different positions that the 1 can be moved into. Yeah? And so that's exactly right. This is another one that you really want to memorize. Okay? So guys, if I give you 8 vectors that are if I give you 8 3 by 3 matrices, please don't tell me it's a basis. If I give you 10 3 by 3 matrices, it's not a basis. There is always an exact correct number of vectors, and this is telling us the size of the vector space. As roughly speaking, it's kind of the size, right? The number of vectors that it takes to span the space. Okay, well, you guys are doing pretty good with this, so I'm gonna challenge you one more time. Is everybody reasonable with that? Does that seem okay? I mean, I'm kind of going back to our original vector spaces. We talked about Rn. We talked about n by n matrices. Let's do another one that I know that we've talked about. What about the dimension of the m by n matrices? In other words, the matrices, they don't have to be square sizes. So you could have something where there's a different number of rows and columns. And if you need to think about an example, you could think about maybe a 2 by 3 matrix or something like that. Does anybody think they might have a guess for what the dimension of this would be? And keep in mind, it should be consistent with the answer we just gave right here. It should line up with that. So what do you want to put here? M times n. Not just something like that. That is it. that is the right answer. Yes, the m by n matrices are 6-dimensional, right? And so just as an example within the example, right? The standard basis for, let me just make one up here. Let's do m 3 by 2 of R. Right, what would that be? Well, there's going to be 6 vectors. The first one is going to be 1 0 0 0 0 0, and then comma 0 1 0 0 0 0, and then comma. The next one's going to be 0 0 1 0 0 0. Sorry for all the writing. To write this all out. The next one is 0 0 0 1 0 0. The next one is 0 0 0 0 1 0. And the last one is 0 0 0 0 0 1. That's going to be it. So you got 6 basis vectors there. And guys, again, if you were to smear each one of these as a single column of a big matrix, you would be writing down a 6 by 6 identity matrix, right? Right. So if I wanted to really test, are these a basis? I would put the first vector into the first column just like that, right? And then the second vector would be this one. The third vector would be this one. So we're just rinsing and repeating the same thing we did before. The pivots are going to go all the way down the diagonal of that 6x6 matrix. Easy peasy. Okay. Well, you guys are getting all of these right so far. So let's see if I can throw you off. What would be the dimension? Let's think about the dimension of Pn of R. Polynomials. So I haven't really done one of those yet. It might actually help to get a specific one up here to look at. Let's just think about P2 of R. Can anybody think of a basis? I know I'm kind of switching gears on you here on a fairly sudden manner, but I'm wondering if anybody could think of some polynomials that they think would span P2 of R. And remember, P2 of R, that's ax squared plus bx plus c. Anything of the form ax squared plus bx plus c. And the question is, could we span all of these quadratic polynomials with some, basis polynomials here? Maybe if we can figure this out, then we can like generalize it up to here. Anybody who thinks they might know, somebody that I haven't heard from yet, that might know what would be a spanning set for those quadratic polynomials? Say it again. Oh, you're jumping back to this again, and you're right. That is the answer. But what's your basis here? What are the three? Since he stole my thunder, we were supposed to do the example and then look at it and say, oh well, then what's the number supposed to be? But we have the number now. So for P2 of R, the dimension is supposed to be 3. So can somebody give me 3 polynomials that would span everything that looks like ax squared plus bx plus c?
X squared, X and 1.
That is beautiful. X squared, X and 1. Do you guys agree that ax squared plus bx plus c can basically be broken down as the span of x squared, x and 1? Not only that, guys, this is actually not just a basis. This is what we would call the standard basis for P2 of R. I mean, think about it. How would we put these into a matrix? Well, we would take the first vector and we put it into the first column. Well, how's that going to look? 1 times x squared plus no x and no constant. And then the second polynomial is just x. Well, that has no x squareds on it. It has 1x and it has no constant on it. And then my 1 here on the end, well, there's no x squared, there's no x, and there's a 1 there. Look at that. That's the identity matrix, which aligns itself with the standard basis for that vector space. Okay? Does it seem reasonable? The dimension of P4 of R would be 5. The dimension of P8 of R would be 9. You have all of the powers of x up to that top power, but don't forget about the constant term, which sort of adds 1 to the answer. It adds 1 to the answer. Okay. So all of these formulas that are in the boxes over here, you guys need to know these cold. Like, I can't emphasize that enough when I teach this class, and usually everybody does it, and I don't have a problem with it, because you really can't survive in chapter 4 if you don't know these basic dimensions. So something to get flashcards for, or if you're good at memorizing things, I would just memorize these numbers so that you just have them. You just want to have them handy. Okay, it's making some sense? Okay, well now, before we get too excited about all of this, we now know what the correct number of vectors is for our vector space. In other words, if we want to find a spanning set that is as cheap as possible, we now know how many vectors that is, right? For all of these examples that we've done so far. Okay. Now, I haven't gotten into weird examples yet, like what about the symmetric matrices? Or what about polynomials that have a derivative of 0 or something like that, right? I haven't gone away from just these are just the big universes that we always have in the background. And I could also ask you, well, what's the dimension of that null space? Or what's the dimension of the span of those vectors over there or something like that? I could ask the dimension of really anything. Anything that is a vector space will have a dimension. Okay. But the thing I want to address with you for a minute here, guys, is what if we are given the wrong number of vectors? What can we say in that case? And I would like to sort of make this as a remark here. Let's suppose we are given k vectors. And I'm going to call this, I guess I'll call this set S again. S is going to be V1, comma, V2, comma, dot, 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 up to Vk. So I know I'm switching the letters on you here. Instead of N, I'm going to call this K for a little while. But somebody hands us K vectors, right? And what I want to talk about here, guys, is how does that K, I'm going to make 3 remarks. How does that K compare with the dimension of V that we're working in, right? So the first one is, if K is bigger than the dimension of V. And guys, that would be if I gave you too many vectors. So I give you, this would be, for example, 10 vectors in P8 of R. Or this could be 7 vectors in M3 by 2. Or maybe it's just 5 vectors in R4. I give you too many vectors. Of course, that means that we've spent too much money. That actually will mean then S cannot be Li, cannot be. Think about it. Your matrix is going to look, well, let me put this over here. Yeah. So S cannot be Li, and I'm just going to add over here parentheses. It might span V. We don't actually know that. It's a maybe. You would actually have to put the vectors into the columns of your matrix and do the EROs to see whether there are pivots going into the far right column. But guys, it is game over immediately in terms of being a basis. It cannot be. There's too many vectors here. And specifically what goes wrong? They are not Li. They are too expensive. And if you laid them out into a matrix, guys, your matrix would look like this. It would be, too many columns, right? There would be K columns here compared to the dimension of V, which is really just filling up the slots of each of these columns. You have a matrix that is very wide. And guys, if you have a matrix like that, okay, here's my bar, and then I have my 0 and number symbols here. If you have a matrix like this, just think about it. You cannot cover every column with a pivot. You don't have enough pivots. It's too wide of a matrix. You don't have enough pivots. If you don't have enough pivots, then I guarantee that you have free variables, which is bad because it means the vectors are LP. They cannot be Li. That's the point. Is everybody with me on that? That's my first remark. You guys are going to want to memorize this as well. Okay. I actually have this on a handout that's in Canvas. I will be pointing that out to you soon. The second remark is, what if I don't give you enough vectors? So Kate, the second remark is, what if the number of vectors in the set is less than the dimension of the space? So of course, just so you're aware, Just so nobody thinks I'm pulling this out of the sky, we already did one of these tonight. Right, it was warm up number 1. You don't need to write this down, but it's already in your notes. We had P2 of R, and then we had x squared minus 2x plus 5, and we had x squared plus x plus 7. So 30 minutes ago, we wrote that down, and I asked you, is it Li? Does it span V? Is it both, or is it neither? And at this point, guys, the dimension of V is 3, right? Dimension of V is 3. What is K? How many vectors did I give you? 2. So 2 is less than 3. We already saw when we worked this out that these vectors do not span V. And in fact, if you don't have enough vectors in the first place, then S cannot span V. It has no chance of doing that. And in this case, I will say that they might be Li. This is not a slam dunk. It is a maybe. They might span, they might be Li, but for sure they will not span V. So guys, if I give you the wrong number of vectors, you don't have a basis. If I give you too many vectors, they're not going to be Li. If I don't give you enough vectors, they're not going to span V. Something is going to go wrong. Okay? The only way that you have any chance of having a basis is if the number of vectors is correct. So what if K does match and does equal the dimension of V? Right? Let's be careful here. So now I've given you the right number of vectors. Does that mean that they're automatically a basis? Here was a good example of that. These 4 matrices right here in M2 of R, that was the correct number because the dimension of M2 of R, we've now established that that's equal to 4. And I've given you K of value of 4. And when I lay them into this matrix here, it is a square size matrix, but did we just go ahead and say it was both right away? No, we did a little bit of other work, didn't we? We actually stopped and said, well, we better take the determinant of that because I want to know whether those pivots are going to go down the main diagonal or not. Guys, in this case, we cannot just say that it is automatically a basis. What I can say here is that S is both or neither. So on that sort of 4-part multiple choice, options thing, the questions I've been asking, it's either going to be a basis, but if it's not a basis, it's going to crash hard. It's going to fail to be both Li and a spanning set. Okay. I mean, just as a quick example, I'll make one that's super easy. What if V is R3? And what if S is the set 1, 1, 1, 2, 2, 2, 3, 3, 3? It doesn't get much easier than this. Yeah, that's the right number of vectors. 3 vectors in a 3-dimensional space. But guys, when you lay those into your matrix here, 1, 1, 1, 2, 2, 2, 3, 3, 3, and then you augment this thing out, right? Well, you can see right away that the first row is fine, but below that, you're going to be zeroing out everything below that. And so, of course, what happens is you get your pivot over here, and you get some free variables here and here. And guys, this is a lose-lose situation. You are not spanning your space, and you're spending way too much money in the process. And of course, if you had taken the determinant of this, you would have gotten 0. In fact, we should add that down here. We should add that in remark 3. It is both if and only if the determinant of A is not 0, and it is neither if and only if the determinant of A is 0. Oh. Righto. Questions there? So just to kind of summarize this really quick, and then we'll take a little break here. I like to kind of have that remark in the front of my mind there, the three-part remark. If you don't like it listed out like that, it can kind of give you another way to draw this remark out, which is what you can do is you can make a little table with me here. Spans V, and then we can do Li, and then we can do both, and then we can do neither, like that. So just make those are the four options, right? This multiple choice question, I give you a set of vectors. I say, do they span V? Are they Li? Are they both? Are they neither? And then up here I'm going to make three columns, guys. I'm going to make three columns here. The first column, I'm going to, sorry, I need to make one more header up here. I'm just making a little table to help you keep track of this. So if K is bigger than the dimension of V, we'll go ahead and put that into the first column, and then the next column, K is less than the dimension of V, and then the third column is going to be K equals the dimension of V. So this is how I would want you to set up this table. So just keep in mind that usually you are going to know the dimension of V ahead of time. If you've done your homework, if you've memorized all these numbers, right, you will know your dimension ahead of time. You're also going to know what K is because you just count. How many vectors did they give me, right? Just count them up, right? So 1, 2, 3, 4, 5, 6 vectors. Okay, you can do that. K is just that number. So you're going to know which column you're in. Just by, if you know what the dimension of your vector space is from some of these things we've put in these boxes, and if you know how many vectors you have, you're going to know that. When K is too big, when K is bigger than the dimension of V, guys, these two are a no. That is a no. It is definitely not Li, and therefore it's definitely not both. If K is too small, then for sure those vectors do not span the space, which means they also can't be both. Okay. And if I do give you the correct number of vectors, so like on that example on the top right over there, a 3-dimensional vector space with 3 vectors given, then it is both or neither. In other words, these two are no. It's not only going to span V. It's not only going to be Li. It has to be both or neither in that case. Do you notice that neither is always an option? Doesn't matter what the problem is, that is always. Sometimes I get students who will say, oh, K doesn't equal the dimension of V, so it's not both or neither. And I'm like, no. What you mean to say is that it's definitely, I mean, if K equals the dimension, it's, what was I saying? I get students who will say that they're in one of these two columns, and so they'll say it's not both or neither. What they really mean is it's definitely not both, and one of the other two is false, but the neither is always an option. Basically, the rest of this has to be filled in with question marks. What you have to do in the rest of that table is literally do the EROs, or if it's a case of the last column, take the determinant, because in that case you'll have a square matrix. See what I mean? So this is how this game gets played. But the dimension of a vector space is really measuring its size somehow. It's going to be a measure of the size of that vector space. Now, to be able to use this table, you have to know the dimension of V. Now, some of them I expect everybody to know cold, or I will very soon expect everybody to know those cold. But what if V is null space of A? Well, that could depend on what the matrix is. We may not know that number ahead of time. So if you don't know the dimension of your vector space ahead of time, then this chart and kind of the remark that that goes with it really can't be quite as helpful. If you don't know sort of what's the right number of vectors for your basis, then, of course, you're not going to be able to take full advantage of this. But at least this is good to know it in the cases when you do know the dimension of your vector space. If you don't know the dimension of your vector space, well, then you just have to figure it out. Are the vectors Li and do they span V? Throw them into the columns of your matrix, do your EROs, and circle your pivots. Just all that good old stuff we've been doing for more than a month now. Yeah. Okay, any questions on any of this? If not, let's take a 10-minute break. I'm gonna let you guys stretch your legs a little bit, get some fresh air. Whatever you want to do to kind of stretch out, this is a good time to do it.
Yeah. Well, there is like this one, it's just-
Yeah. That would be, make sure you circle. But yeah, circle the pivots would be helpful, but yeah, I guess so. So, I mean, that's basically what you're basically saying, realizing is what this mark is. Hey, that's the definition of the.
Yeah.
You're for sure going to get a pivot that goes in.
Yeah.
I forgot to draw that. And so. Once you know the other two, I guess it's more like.
Are you able to like make the sequences in series on them? Like matrix?
Yeah, you can do all that stuff. I'm not gonna talk to you about it right now.
No, yeah, it's fine, it's fine. I was just
That
curious.
is actually in the book.
Oh, it is? Oh,
Yeah,
okay.
yeah, you'll find that, I forget where it is. Chapter 7, I wanna say.
Oh, okay, okay. I just got curious.
Yeah, it's introduction to the matrix exploration. So I'm taking the powers of matrices here and creating a series of that. So you can take a look at 7.4.
Okay. Yeah, I just got curious.
Yeah, of course.
He's like, I can do it on. Yeah, I have a thing going. Someone played a phone, so it's something
How's your daughter?
Oh, cute.
Yeah.
Cute as ever.
Getting bigger.
Yeah. Put her in one, it's like, it consisted kind of goalie things, feet already touched it.
Oh,
I gotta get out my shame. Anything, and that's so recent.
it seems so.
What's that?
With my.
Oh, with my class.
You just like slam your phone. I was like, there you go.
Not about this, not about this, okay. I'm like-
Like wide awake.
Alright.
It's like bedtime.
Yeah. That's perhaps sushi. So it's. I just read good place when you does make sense. It's almost September 11th. And we could have it for 12 because he's going to schedule a C-section.
Uh-huh.
And then if you got cramps yet. So like, coming down.
Is that the class?
No, my blood pressure.
Oh, yeah.
Yeah. That's like dangerous for both parties.
Yeah.
Wait a minute, this is. It's just fine. Yeah, it was so easy. It's like 15 minutes.
It's like fun.
It is, it's crazy, it's like, all right.
Time. Yeah.
Ever an injection?
Did that hurt?
Yes, she said that was the worst part. Is the injection.
Yeah, that was like.
That's what- And they said that West music, so she like massage, like piano music. I was like, this opportunity for my rock and roll, and my heavy metal. I wish they did like that. Awesome.
Oh, God.
No, it was like. She was 6 September. She's. Yeah, so we'll see.
Yeah.
Tired all the time.
So.
All the time.
Kind of the same, but one more. The feels the same.
Yeah, I think it kind of goes to just like emotion.
Yeah.
of it. Wasn't getting out there.
From last time. We went to the side. I was there. But basically just went over like writing the stuff. Oh. I don't know. It's 2 hours. I mean, it's there.
Yeah.
I thought, yeah, I was like,
All right, everybody, I think I've got just about everybody back now. I'm hoping that's the case. And I see there's a few problems on the sideboard over here, so I want to save a little time to help you with those. Does anybody have any questions though on what we sort of said during the first part of our class tonight? Seem pretty reasonable. In a nutshell, this is what you're going to want to know. And this works great if you know what the dimension of V is. Trouble is sometimes you don't know what the dimension of V is ahead of time, in which case this table really just can't be used. Okay, but when you know the dimension of V, it's really nice to keep that in mind. I'm going to move on and try and spend maybe a very short amount of time. So we're skipping section 4.7. These two sections, they're pretty fast and they kind of go together. So I'm going to kind of do them all in one big breath here. And this won't take very long. One of my most popular YouTube channels is or YouTube videos, I should say, is me talking about this topic, and it's only a 20-minute video. So I know that I have at least once done it in 20 minutes. So let's see if I can do this one in 20 minutes. James is going to time me.
Yeah.
I can see that already. Okay.
Yeah.
So we'll see. What we're going to do here, guys, is we're going to fix any matrix at all. Any matrix at all. I'm going to fix a matrix A. And I want to talk about 3 subspaces that we can associate with any matrix. Okay? These are pretty important. Linear algebra folks will talk about these all the time. The first one is actually the one you already know about, which is the null space of A. And I'm just going to remind you again what that is. I went over this in that video that you watched a couple of weeks ago, but just to kind of get it back in mind again, this is the set of vectors X from Rn such that A times X is equal to 0. Okay. So this is the null space of a matrix. I won't spend too much time on this because, well, you already know about this one. This one, one of the things that we already know about it is that it is a subspace. Whenever you say something is a subspace, I always like to say, of what? It has to be a subspace of something. It has to be inside of some universe. Can somebody tell me what the null space of A would be a subspace of? Say it again. It's right here on the board, Rn, right? These are vectors in Rn. So it is a subspace of Rn. That is correct. And so because it's a subspace, it is a vector space in its own right. Because it's a vector space, it has a dimension. Okay. So I'm just going to give you a quick definition here that goes along with this. This part is maybe perhaps new. We refer to the dimension, I'll just say dim of null space of A, as the nullity of A. So that's a new word. The nullity of a matrix is just the dimension of the null space. So that's a number. It is some kind of a number and we can calculate it. Maybe I will do an example really quickly here for you. Let's say I take this matrix A. I'm gonna just do one example. Let's say we have 1, 2, 6 on the first row, and then 2, 1, 6 on the second row. The third row, 0, 1, 2, and the fourth row, 1, 0, 2. And what I propose that we do here is let's see if we can find a basis for the null space of A. So we talked about a basis. Remember, a basis is just a set of vectors that is both Li and spans the vector space that we're talking about, in this case, the null space of A. So I need some vectors that will span the null space of A that are also Li. Has to be both. We're talking about a basis. We're talking about this row of the table. And so we don't know what the dimension is. Well, we're calling it the nullity of A, but we don't know on this example what it is. So we're gonna have to do some calculations here. So let me give a little solution here. Remember how the null space works? You take your matrix A and you augment it with a column of zeros on the right side. So let me just do that here. We take 1, 2, 6, we augment that with 0. Then we take 2, 1, 6, we augment that with 0. Then 0, 1, 2, augmented with 0. And 1, 0, 2, augmented with 0. Okay, and we have to do a quick little bit of EROs here. I'm going to do this pretty quickly, guys, just to save a little bit of effort. The first row is going to stay the same. I'm going to move the third row up to the second row. So that will give me a 0, 1, 2 there. And then I'm going to have you guys just take my word for it or check it on your own that the remaining rows just get all wiped out with zeros. So I'll let you check this again. This has to be verified with, 2 or 3 EROs. It's not much. It's not too bad. So I'll let you guys check that. So the null space is the solutions to this. And as you can see, we have some unknowns here. Let me call them A, B, and C. Or you can use X, Y, and Z, doesn't really matter. But the point is that we do have a free variable, which in my notation is C. I'm going to call that T. I usually like to relabel my free variables with R, S, or T, something like that. So I'll use a T for this one. And then I have to, go through the back substitution process. The second equation, second row, I should say, tells me that B plus 2C equals 0. So if you solve that for B, I think we can do it in our head, right? Negative 2T. Okay. So that looks pretty good. And then I've got to figure out the first row, which is A plus 2B plus 6C equals 0. I've got to figure out what A is. A is equal to negative 2B minus 6C. So that's negative 2 times negative 2T minus 6T. And I'm just scribbling it out. It's negative 2T. Okay, so A is also equal to negative 2T. Okay, so anyway, is it okay if I just erase this little chicken scratch? Didn't keep it up there very long, but it's not bad. You just do the back substitution here, right? So then your null space of A is the set of vectors, and you might remember when we did one of these last week, I like to draw them as columns. Negative 2T, negative 2T, and T, written out as a column. And this is going to be such that T is an element of the real numbers. That's how you would write it. And so I would like somebody to propose for me what my basis for my null space is. I've written down what the null space is. The question is, what will be the basis for the null space? Right. Do you think they know how to do that? Or at least to figure out what would be a spanning set? How quickly the material, it's 3 sections ago, so it feels like an eternity, right? When you want to find a spanning set for a vector space, what do? Write down the form of the vectors, bust out the variables, and make a list of the vectors that are left behind. Remember I think I called this step A, step B, and step C. It's actually what you're doing on tonight's homework, right? Find a spanning set for a vector space. Write down the form of the vector, bust out the variables, and write down the list of the vectors that remain. Well, I'm gonna just jump straight to, if I bust out the T, right? If I bust out the T, what am I left with? -2, -2, and 1. And guys, if I only have one vector, it's obviously Li. Okay, I can't get rid of that vector and expect to have anything left. So that's it. That's it. Based on that, guys, what is the nullity of this matrix? The definition of the nullity is it's the dimension of the null space. The dimension was the number of vectors in a basis. How many vectors are in the spaces? 1, right? So this is just 1. Make sense? Now, I want to pursue this a little further. Why was it 1? We had 1, it was the dimension of this null space was 1 because there was 1 vector being busted out. If there had been other free variables, we would have had more terms more things to bust out, right? See, here we only have 1 free variable. That's actually the point. There's only 1 free variable here. Why is that? Well, that's because there's only 1 column without a pivot. So because there's 1 unpivoted column, that's why the nullity is 1. I just want to remark this really quick. Right, the nullity of A, because it's nice to kind of figure out what these dimensions are ahead of time if you can. The nullity of A is the number of unpivoted columns of the row echelon form of A. That's always true. This is always true. Because for every unpivoted column, you're going to introduce a free variable. For every free variable, you're going to be busting it out and leaving behind another vector. Now here we only had 1. 1 unpivoted column gave me 1 free variable, which gave me 1 vector to variable to bust out, leaving me 1 vector left over. And that's why the dimension was 1. Okay. So, that's interesting. The number of unpivoted columns is called the nullity. Did we have a name for the number of pivoted columns? It was the rank. It was the rank of the matrix. In this case, this matrix has a rank of 2. So you ready for the easiest theorem in linear algebra? If you add the rank to the nullity, okay, the rank is how many columns have pivots. The nullity is how many columns don't have pivots. Altogether, that would have to be all columns. Every column either has a pivot or it doesn't have a pivot. This is the statement of a fairly famous theorem that is kind of a no-brainer, to be honest with you. It is called the rank nullity theorem. And I'm going to state it right here, guys. Okay. What it says, guys, is that for any matrix A, and again, we'll assume it's M by N. For any matrix A, the rank of A plus the nullity of A adds up to, what's going to add up to? Total number of columns, which is what? Look at the size here. What is it? Is it M or is it N? N. Thank you. It is N. It is N. Guys, that is the equation. That is the equation. So if you want to know what is the dimension of the null space of your matrix, one way to figure that out is to just take however many columns you have. Right, you're going to know this number. You're always going to know this number. So these other two numbers just have to add up to n. So if you know the rank, then you'll know the nullity. If you know the nullity, you'll know the rank. It's the easiest equation in the world, and it's so easy to explain it too. The rank is the number of pivots. And the nullity is the number of non-pivots in terms of columns, if I think of it in terms of columns.
I want to have a question, go back to the remark real quick.
Uh-huh.
About that one is number of unpivot, right?
Yeah.
So on that one, we have up to like 2 number of unpivot, which is not 2 columns. So why we only have 1?
Well, we have only one unpivoted column.
Oh, okay.
I have pivot here and here. The first 2 columns both have pivots. So on this example, the rank is 2, the nullity is 1, and 2 plus 1 is 3, which is n, right? This matrix is 4 by 3. Yeah, so n is 3 here on this matrix. That all good with everyone?
I see the 4 columns. I'm mistaken with that.
That's okay. So far, so good? Okay, really quick, let me talk about, I said there are 3 subspaces. I've talked about the null space, which really was mostly a review, okay? So you can see how one of these problems would work. You just do your EROs, circle your pivots, set up your free variables, bust those variables out, and there's your basis. Pretty easy. Okay. Let me get on with the second. How much time do I have left, James? 3 minutes? This took 17 of my 20 minutes? I can't believe it. Oh my gosh. All right, in that case, I'm just gonna claim that I'm getting slow in my old age. So we're gonna spend more than 3 minutes on the rest of this. The second one that I want to talk to you guys about is something called the row space of A. The row space of A. And what is this going to be? By definition, so this is something new. We haven't talked about this yet. This is by definition, so I'll put the definition above the equal sign here. It is the span of the row vectors of the matrix A. By definition, it is the span of the row vectors. So, because it's called a row space, you're probably thinking it is a subspace, and you would be right. It is a subspace. Can somebody tell me why I would know that this is a subspace? I see that word span. Remember, if anytime I take the span of anything, I don't care what it is, it will always be a subspace. So this one is definitely going to be a subspace. And again, I'm going to try to get a handle on what it is a subspace of. And if we need to help ourselves out with that, we do have an example here. So if I look at these row vectors, right? What universe do these rows live in? Say it again. R3, right? R3. So is the 3 lining up with the M or with the N in my notation? It's N, right? It's still N. It's actually the same as the null space is a subspace of Rn. Well, guess what, guys? So is the row space. This is also a subspace of Rn. It is also a subspace of Rn. That's exactly right. Okay. So let me write down how you would get a basis for this, because we wanted to find a basis for the null space of a matrix. Now we should at least also explain how to get, I'll put this here, guys, how to get a basis for the row space of A. Because this is ultimately gonna be the important thing. This is what we're gonna wanna be able to do. So, I know, for example, here. In fact, let's, on the side, let me come back over here. On the side, I wanna play with this example. So give yourself some room to fill in some notes over there, but I also wanna look at our example. In our example, with the same matrix that we've been looking at, the row space of A, so this is just from above. Same example as from above. The row space of A is the span of the rows of A. The first row of A is 1, 2, 6. The second row of A is 2, 1, 6. The third row of A is 0, 1, 2. And the fourth row of A is 1, 0, 2. That's it. So that's great. So I'm gonna have a question for you then. Does that mean that these are going to be a basis for the row space of A? Well, I'm gonna give you a little clue. The dimension of a subspace can never be more than the dimension of the universe that it's in. And in this example, the row space is a subspace of R3. For this example, n is 3. So the dimension of my row space is not going to be more than 3. It can't be, because those are vectors that are living in a universe whose dimension is only 3. So if I see 4 vectors, okay, back to that chart that I just erased, 4 vectors in R3, guaranteed they're not a basis. It's too many vectors. This is too many vectors. It's not going to be a basis. In fact, I can tell you already that it's LD. Right? If K is bigger than the dimension that you're supposed to have, they are LD for sure. So it turns out that you cannot, be careful with this because I will almost certainly ask you this question. I will give you a list of vectors. I'll throw the word span in front of it, and I'll ask you what's the dimension of that thing. It is a subspace, so it has a dimension. And the wrong thing to do is to just count up these vectors and use that as some kind of a total and say, oh, that's the dimension. It's not ever that simple. What we actually have to do is we have to recognize that there could be linear dependencies here. And in fact, when I took this matrix and I started doing the EROs here, those EROs actually exposed some linear dependencies because we ended up getting some rows of zeros down here. You see, these rows of zeros down here at the bottom of this matrix, they are basically telling us that we have massaged out linear dependencies that existed among these vectors in the first place. The answer to how to get a basis for the row space is the following. You take A, you do your EROs, you get the row echelon form of A, right? And then what you're going to do here, guys, is you are going to take the non-zero rows of this row echelon form for your basis. You just throw away the rows that got zeroed out. So in this ERO process, guys, we zeroed, I know I didn't show all the work here, but we ended up zeroing out a couple of rows. You know why that happened? It happened because our EROs exposed those linear dependencies and left us just with the non-zero rows that we could use as our basis. So in our example, a basis for this row space, let's just add it right here, is just to take the row echelon form and just grab those first 2 rows, the non-zero rows of the matrix. It is the non-zero rows of the row echelon form. of A. Now, there's a beautiful thing here that I don't know if you realized. But if I ask you to give me a basis for both the null space and the row space, for both of those questions, you just need to get to the row echelon form here. You don't have to do the EROs twice. Just take this matrix. For the null space, we're gonna, what? Introduce free variables and do back substitution. For the row space, we're just gonna take the non-zero rows of that row echelon form. That's right. And what is the dimension, by the way? Just in general over here. The dimension of the row space of A. Anybody have an idea about that one? I know it's equal to 2 here. You can count. The number of vectors in a basis is 2. What is it going to be in general? How many vectors am I going to be taking? I'm taking all of the non-zero rows of my row echelon form. Here's my row echelon form. I take my non-zero rows, right? What can I count that sort of lines up with how many non-zero rows I have? The pivots, the rank of the matrix, that is exactly it. The dimension of the row space of A, my friends, is just the rank of A. That is exactly what I was looking for. It is the rank of A. Beautiful. And so here, in this case, the dimension on this specific example, the dimension of the row space of A, it is exactly 2 for this example. That's right. Make sense? Okay, not too bad. There's one more. I'll get this done. I'm going to very quickly talk about the third one. I'll probably come back to this again on Thursday. We're doing great. We'll have just a little bit left over to finish on Thursday. But let me put down number 3. So we have the null space. We have the row space. Anybody have a guess what the third one's going to be? One more time. The null space, that's the first one, null space. The second one is the row space. Call space, is that what you said? Sorry, call space, I just can't hear. Columns, yeah, the span of the columns. Instead of taking the span of the rows, we can take the span of the columns. That is exactly right. Let me put that down. Number 3 is, it's called the call space of A. And by definition, guys, this is just the span. This is just the span of the column vectors of A. And again, why is it a subspace? Because it's a span. Exactly. So this one is also a subspace. But this one is a subspace of what? If we look back at this example and we start taking the columns here, these columns live in which universe? The columns go up and down. So on this example, each column has 4 entries in it. So that would be what vector space? R4. And how does the 4 relate with the M or the N of the general notation? It's M this time. This one is M. So the first 2 subspaces are subspaces of Rn, but this one, my friends, is a subspace of Rm. It is a subspace of Rm. Okay. And again, just like with the row space, you can't just say, oh, well, I'll just take the columns of the matrix and call that a basis. Because again, the vectors might not be a basis after all. So we actually have to do another process where we actually have to take, we actually still have to just bring the matrix into row echelon form, but then we have to take the non-zero columns from the original matrix A. You can't use the row echelon form matrix for that. So I'm going to come back to this on Thursday and wrap up this one. So stay tuned. On our next class, I will fill that in. We're almost done with chapter 4, finally. And we can talk about it some more there. Okay, but that's what it is. I would like to spend like 7 minutes anyway to try to help you with a little bit of the homework. Okay? By the way, there's a handout in Canvas that has all of this summarized. Null space, row space, column space, what it is, what it's a subspace of, what its dimension is, it's all in there. I'll send that out to you guys in an email so you can have it easily accessible. But let's spend a few minutes talking about a couple of these homework problems. Half the time with the homework, I think it's just, what is the question asking? It's kind of what's going on. Let me start with number 31. These are gonna go fast. These are gonna go lickety split, okay? Partially because I have to go fast. Let me start with number 31 in section 4.5. What it does on this problem, this is on tonight's homework, P2 of R, and they give you these polynomials, 2 plus x squared, 4 minus 2x plus 3x squared, and then 1 plus x. And what the question says, it's a little weird. It says, determine a linearly independent set of vectors. So it says, find a linearly independent set with the same span as S. Just kind of writing it in shorthand. It's supposed to span the same thing as all of S. So it turns out that these three vectors are not Li. You can put them into the columns of your matrix, as we so often have done. So remember, if there's no x term here, that means you need to put a 0 in the x position in that first column. The second one is going to be 4, -2, 3. And the third one is going to be 1, 1, and 0. All right, and then I augment this with 0 / number symbols, usually the way I like to do it. Okay. And what you have to do here, guys, is you need to bring this into row echelon form. Okay. I don't remember exactly what the row echelon form is. I would probably move the bottom row to the top so that I can get a 1 up there in that top position. And then I would leave the second row the same. And then just because I'm running short on time, I'm going to skip showing you what happens with the third row, but I will tell you now, it completely zeroes out. Take my word on that. By the way, is this set, does it span V? Is it Li? Is it both? Is it neither? Well, we already know the dimension of P2 of R is what?
3.
It's 3. What's the K value? How many vectors did I give you? 3. So K matches with the dimension. That means this is both or neither. But as you can see, because we got a whole row of zeros here on the bottom, it really means you're going to get a pivot over here. It's actually neither. Okay. So it's neither, but they're asking us to find a linearly independent set. Can we do something with this problem to obtain a linearly independent set, even though these 3 vectors are actually LD? Say again?
Take one of the columns out.
You know, what's really the problem here, guys, exactly what James is noticing, we have a free variable. That's why the vectors are LD. So how could we not have that free variable? We could not have that free variable if that column wasn't there. If that column wasn't there, we wouldn't have any free variable. But if that column wasn't there, that would have meant that you never had this vector in the first place. You go back for a $1,000 refund, and now you just take these two. Guys, this is the answer to number 31. You just keep these two, or it is, sorry, I should say that differently. It is an answer to number 31. Remember, there can be many correct answers. In fact, I don't think this is the one that's in the back of the book. But you don't actually have to write anything down that's not already here. You just list these two, throw this one away. That's it. Make sense? Any vectors that correspond with unpivoted columns can just be thrown away. That's how that works. Good enough? Okay, let me do another problem or two. I've got just another minute or two. So back to 4.4. On number 9. Yeah, on number 9, they give you these 3 vectors here. Guys, just hang on. I'll be as quick as I can here. I just really want to help make your night a little easier. 516 and 602. They first ask you whether these vectors span R3. And that's an easy one. All you have to do, as usual, is put these vectors into the columns of this matrix. And actually, I honestly would probably just take the determinant of it. And what you're going to find out when you do the determinant of this matrix is that it does equal 0. And if it equals 0, that's bad, right? That means that these vectors are neither. They don't span R3, and they're also not Li. But there's a second part to this question, which is something I have not really shown you guys in class, which it says, show that these vectors do span the plane with this equation, which at first sight, you're like, where does that come from? So they give you this plane, x plus 13y minus 3z equals 0, and they say, okay, we'll admit these vectors do not span the entire R3, but can we at least show that they span something? Some part of R3. This plane would be a part of R3. It's actually a 2-dimensional subspace of R3. And so the way you do this problem, guys, is this is the one problem on the assignment where instead of using the number symbols over here in the far right column, which is usually what you do when you're trying to see if your vectors are going to span the space, this is the one problem on the homework where you actually need to use X, Y, and Z, and it is a little bit messy. You're going to need to actually track what's going on in the far right column as you do the EROs. So you will need to do EROs here, and you're going to need to, bring this thing into row echelon form. I'm going to tell you right now what's going to happen. You're going to get a pivot here. You're going to get a pivot here. We've already said that the determinant is 0, and that's because the bottom row is going to become all zeros. But this thing over here, which would have been a number symbol normally in the way I've been doing most of these problems. This expression, if you do the EROs correctly, it should basically be that equation up there. It should basically give you this equation in this little far right column. And see, if that is equal to 0, then it's actually not a pivot. Because 0 cannot be a pivot, you might remember, right? So as long as your X, Y, and Z are on this plane, then this is really just another 0, and you're all good to go. Yeah. The only time when it's not going to span something is if that's a pivot, and that'll be a pivot only if this expression is not 0. So that's how this is going to work. And I can help you later on if you need extra help during the office hours with this, but you do need to be a little more attentive on this far right column, just on this one problem only. The rest of the assignment, you can use number symbols everywhere. So, all right, well, I ran out of time, guys. If you have questions on number 17 or 21, those are both pretty short. I can certainly help you out during office hours with that. But yeah, thank you so much for today. If you've got any questions, definitely check in with me. And I will see you again Thursday.